A very good morning to our lecturer for the subject EPO554. Today, we will be presenting our assignment that has been given to us, which is DC motor speed control with the method terminal voltage control. As for the assignment, we will have three people in this group, which is first myself, Mohamad, Alif, Haziq, Benyamin, and the second one is Mohamad Walid bin Rosli, and the third one is Mohamad Danial Haziq bin Mohamad Kamal. Right, for this part, for introduction, I'll be presenting first. Okay, DC motors are widely used in industrial and electrical applications such as conveyor systems, elevators, industrial machinery, and electric vehicles. In these applications, controlling motor speed is important to ensure a smooth operation, high efficiency, and safe performance. For a separately excited DC motor, the speed is mainly determined by the armature voltage when the field current is kept constant. Therefore, modern motor drive systems use power electronic converters to regulate the voltage efficiency instead of traditional control methods.
Okay, thank you, Alif. Now I will present the circuit diagram with our innovative approach. So first, I want to show our single phase half control rectifier circuit that connect to the motor. Next, the buck converter circuit that connected to the motor. Okay, now I want to show our innovative approach to construct the circuit. Here shown the circuit without using both to and from blocks. So the disadvantage is it is difficult to identify mistake or broken connection because wires overlap and cross. Next is because it have excessive wiring. Now the circuit using both to and from blocks. So we can see the advantage is it reduces excessive wiring, making the schematic more visually neat, easier to trace signal and understand the circuit flow. And lastly, error or broken connection can be identified more quickly. Now I will pass the presentation to Haziq.
Okay, thank you. Assalamualaikum. My name is Mohamad Danial Haziq bin Mohamad Kamal, and I will be presenting the calculation and simulation result for question 1. That is the average output voltage response for the converter by changing the firing angle of the power semiconductor device. So as you can see here, the type of DC motor that we have chosen is a 10 horsepower, 240 voltage VRMS, 1750 RPM speed, and 150 voltage field voltage. So the question is single phase half control. So we use this formula, that is VR average equal to 0.45 VRMS 1 plus cos alpha. Here are the calculation for the phase delay to insert in the pulse generator in the simulation. And here are the tabulated results. As you can see here, the value for the calculation and the simulation are plus minus 2 to 3 difference, because in the simulation there are real resistance in the components. And also, as you can see, when increasing the firing angle, the voltage, the VR average will decrease. So um, it proves that when the firing angle increase, the voltage drops. So next, for the calculation and simulation result for question 2. The motor speed response by changing the firing angle of the power semiconductor device and motor. Here you can see the add-rated calculation. On the left, the calculation for 20.35 Newton meter, and on the right is the calculation for torque 81.41 Newton meter. Here, next, this is the calculation of speed. On the left is the calculation for firing angle 20 degrees using torque 20.35 Newton meter. And on the right, also firing angle 20 degree using torque, but using torque 81.41 Newton meter. So we also use firing angle 30 degrees. So the calculation is just the same as the 20 degrees. Okay, so as you can see, this is the tabulated result. So from these results, as you can see, it doesn't matter how much torque you use. If you increase the firing angle, uh, the speed will decrease. So that's all, and I will pass this to the next person. Thank you.
Alright, thank you. For now, I will be taking over on explaining question number 3. Okay, the question is the motor speed if the terminal voltage are changed by using buck-with duty cycle is vary from 0.5, 0.6, 0.7, and 0.8. Okay, as you can see here, I'll be explaining the buck converter speed control principle first. Okay, the first one is buck converter regulates armature terminal voltage, output voltage controlled by duty cycle. The average output voltage is in the relationship of VE equals to D times V in. And the fourth one is field current kept constant. And the last one is motor speed depends mainly on armature voltage. As we can see here, before we continue with the simulation and the calculation, we need to do the rated motor condition first. Okay, the torque we got 20.35 Newton meter, EMF is 199.89 volt, and for the VT we got 240 volt, and the armature current is 15.54 ampere, and the last one is speed 1750 RPM. The first simulation and analytical calculation that we did is for the duty cycle D equals to 0.5. Okay, comparing both together, we can see that terminal voltage for simulation, we got 118 volts and motor speed is 606 RPM. When we compare those values to the analytical, they are almost the same as the analytical. They got terminal voltage of 115 volts and the speed RPM of 655 RPM, which is similar together. As for the results at duty cycle D equals to 0.6, we can see that the terminal voltage equals to 142 and the motor speed is 829. And terminal voltage in the analytical we are getting around 138 volt and calculated speed of 857 rpm. And once again we can see that the trend of these results are the same. When the duty cycle increase, the terminal voltage and the rpm also increase. Same with the duty cycle at d equals 0.7. At analytical, we got 161 volt for terminal voltage and speed of 1058 RPM. We refer back to the simulation. We got terminal voltage of 166 volt and motor speed of 1053 RPM. The same trend as before. When the terminal voltage increases, the speed also increases, which the effect of uh, increasing the duty cycle. Lastly, we did a simulation and calculation at duty cycle of 0.8. At terminal voltage for calculation, we got 184 volt, while in the simulation we got 190 volt, almost the same. Calculated speed at analytical, we got 1259 RPM. And for the motor speed at simulation, we got 1276 RPM. Based on the calculation of the analytical calculation and the simulation, this is the tabulated result uh, for the question number 3. As we can see here, all the values similarly linearly increase together as the duty cycle increase. As duty cycle increase, the terminal voltage will increase, same as the motor speed. But for the armature current, they will be stay the same around 50.4 throughout the simulation. As for the calculation, they are also the same. As for the field current, they also maintain a same number, which is 1.066 throughout the whole calculation and simulation. As for question number 4, I'll be giving it to the next presenter.
Thank you, Alif. Now I will present the calculation and simulation for question 4. First, we find the value at rated condition. The terminal voltage Vt equal to 240 volt, the torque equal to 20.35 Newton meter, the armature current is 15.54 ampere, Eg equal to 199.89 volt, and Kevlar is equal to 1.091. Here is the example for one of the condition tested, which is at duty cycle 0.5 with 50% load. Here show the calculation result. And now show the simulation result. If you can see, the calculated motor speed is 790 rpm, while the simulation result is 857 rpm. And the armature current shows a small difference of 9.326 ampere for calculation compared to a 10.74 ampere for simulation. These minor deviations can be attributed to modeling assumption and practical simulation effect. The current field, however, remained a constant at 1.066 ampere across the board in both scenarios, indicating that part of the model behave identically. In conclusion, for all condition tests, the results show that increasing the duty cycle will increase the motor speed due to the higher terminal voltage, while increasing the motor load increases the armature current because more torque is required. The field current remains constant since the motor operates with fixed field excitation. Next, the simulation result closely match the theoretical calculation, validating the accuracy of the motor model. For example, at duty cycle 0.8 with 90% load, the calculated speed was 1231 rpm compared to 1327 rpm in the simulation, and the armature current rose from 19.79 ampere to 18.95 ampere. These small differences are expected as they reflect losses and non-idle effect considered the simulation, but overall the agreement demonstrates that both approaches capture the same physical behavior of the motor. Okay, that's all from our group. Thank you.